Many process systems have to be supplied with a variety of fluids in order to operate properly. These fluids, which include liquids and gases, are carried throughout the plant by a maze of piping systems. The flow of the fluids through the piping systems is controlled by valves. Maintenance personnel are responsible for servicing and repairing different types of valves to keep plant systems operating smoothly. Valves are used to control the flow of fluids in piping systems. When a valve is opened, fluid flow begins. When a valve is closed, the flow is stopped. Many valves are designed to operate in either the fully open or the fully closed position, but not in between. In this unit, we'll call these valves on-off valves. In addition to starting or stopping the flow of a fluid, some valves are designed to regulate flow as well. This can be done by partially opening or closing a valve. Valves that operate in this manner are sometimes called either control valves or throttling valves, since they regulate or throttle flow. The largest component of a valve is the valve body. It provides a path for fluid flow through the valve. The valve body can be made of different materials, such as bronze, cast iron, and stainless steel. The material that's used depends on the valve's application. The valve body provides the means to connect the valve within a piping system, and it houses many of the valve's components. One of the internal components is the valve seat. The seat is a stationary component of the valve, and it can be threaded, press fit, or welded into the body of the valve. In some cases, the seat is cast as a component of the valve body. In high-pressure, high-temperature situations, the seat may be both threaded and welded to prevent leaks. The seat is used together with a movable component called a disc to control flow through the valve. The disc is attached to the stem, and the stem connects to the hand wheel. The hand wheel is used to screw the stem in and out, which in turn lowers or raises the disc. If the hand wheel is turned in the open direction, the stem moves up and the disc moves away from the seat. As a result, flow through the valve is increased. When the disc reaches its limit of travel, the valve is fully opened and maximum flow can pass through the valve. If the hand wheel is turned in the closed direction, the disc moves down toward the seat and fluid flow is reduced. When the disc presses tightly against the seat, the valve is fully closed and flow through the valve is stopped. In order to maintain a leak-proof seal, the faces of the disc and the seat must be smooth and fit together perfectly. The removable bonnet is designed to allow access to the interior of the valve and to provide a leak-proof seal. It also supports the other valve components. The bonnet can be bolted, threaded, or welded to the valve body. At the point where the stem goes through the bonnet, there's a recessed area called the stuffing box. The stuffing box holds the packing. The purpose of the packing is to prevent fluid leaks from the interior of the valve, while allowing the stem to move freely through the bonnet. The packing is made of a material that can be compressed to form a tight seal around the stem. To compress the packing, a component called the gland follower is attached to the valve. The gland follower can be bolted or threaded onto the valve bonnet. When the gland follower bolts are tightened, the packing is compressed to prevent leaks. Valves come in many shapes and sizes, and they can be used in many different applications. The way a particular valve is identified can depend on factors such as its physical characteristics or how it's being used. Among the common ways to classify a valve are by the shape of its disc, by the shape of its body, by its function, by the conditions under which the valve operates, and by the method used to connect the valve within the piping system. Keep in mind, though, that valves are often identified using more than one of these classifications. This valve is called a ball valve. It's identified by the shape of its disc, which is a ball. Another example of a valve that's identified by the shape of its disc is this needle valve. It has a narrow, pointed disc that's shaped something like a needle. This valve may be identified by the shape of its body. Because it has a globe-shaped body, the valve is called a globe valve. This valve is identified by its function. It's a fuel flow control valve. Its purpose is to control the flow of fuel entering a furnace. This is an example of a valve that's identified by the conditions under which it operates. It's called a high-pressure steam valve. During operation, the valve regulates flow through a high-pressure steam line. Some valves are identified by the way they're connected to the piping system. For example, this flanged valve gets its name from the fact that it has flanges that are bolted to the piping. Similarly, this threaded valve has threaded connections for joining it to the piping system. And this welded valve is welded to the piping. The same valve can often be identified in several different ways. For example, this valve can be called a fuel flow control valve because its function is to control the flow of fuel to a furnace. It can also be called a globe valve because of the shape of its body. And it can be called a flanged valve because of the way it connects to the piping system. Gate valves are primarily used for turning fluid flow on and off and for isolating equipment. They're normally installed in applications where straight flow is desired. A gate valve generally has a relatively long body and stem, which extend some distance beyond the piping that the valve is connected to. A gate valve typically has two seating surfaces and a disc that fits between them. The disc is raised and lowered, like a gate, to start or stop the flow of fluid through the valve. This valve has a wedge-shaped disc. When the closing point is reached, the disc is wedged tightly against the valve's seating surfaces and flow is shut off. Sometimes a wedge-shaped disc is split down the center and the two halves rest independently on opposite sides of the valve seat. Small gate valves generally have fixed seats that are cast as part of the valve body. It's more economical just to replace these valves than to repair them when they're worn or damaged. Large gate valves, however, frequently have replaceable seats. With these types of valves, it's less expensive to replace the seat than the entire valve. Many gate valves have what is called a rising stem. In most cases, the stem rises as the hand wheel is turned counterclockwise and lowers when the hand wheel is turned clockwise. The amount of stem protruding from the hand wheel indicates the position of the disc. If the stem is all the way down, the valve is closed. If the stem is all the way up, the valve is open. On a gate valve with a non-rising stem, the stem and hand wheel rotate together. The disc is threaded to the lower portion of the stem. The disc then moves up or down the stem as the hand wheel is rotated, but the stem does not move up or down. Because no allowances for stem movement are necessary, a non-rising stem is useful in applications where space is limited. Gate valves work best when they operate in either the fully open or the fully closed position. When a gate valve's disc is completely raised, fluid flows straight through the valve with little obstruction. However, if the disc is partially raised, a space opens on either side of the disc and fluid passes under the disc. This type of flow creates turbulence and causes the disc to swing from side to side, banging or chattering against the seating area. The chattering quickly leads to wear on the seat and the disc. Eventually, the damaged valve won't be able to shut off flow even when it's fully closed. Also, the flow of fluid through a partially open gate valve wears the disc unevenly. In time, the edges of the disc that are most exposed to the flow become eroded, and the disc can no longer seat properly. The seating surface, body type, and disc arrangement of a globe valve vary according to the design and function of the valve. For example, an angled globe valve, or angle valve, has a globe-shaped body with an inlet and an outlet at right angles. This design enables the valve to change the direction of fluid flow. Using an angle valve eliminates the need for the additional piping that's normally required to change the direction of flow when other types of valves are used. Several different types of discs are commonly used in globe valves. This is a standard or conventional type disc for a globe valve. The disc seats against a tapered, flat-surfaced seat. A globe valve with this type of disc is generally used in either the fully open or the fully closed position. It can, however, also be used for moderate throttling or regulating of flow. Globe valves with conventional discs are normally used in low-pressure, low-temperature systems. This globe valve has a composition disc. This type of disc is replaceable, and it comes in a variety of materials for different types of service, such as high and low temperature water, air, or steam systems. The seating surface for a composition disc is often formed by a rubber O-ring or a washer. This globe valve has a plug-type disc. The disc is cone-shaped, and it fits into a cone-shaped seat. This design gives a wide seating area that makes the valve suitable for throttling flow. Also, the valve can be used for a wide range of pressure and temperature conditions. Needle valves are generally smaller and longer in relation to their piping than other types of globe valves. As this cutaway illustration shows, a needle valve's seat opening has a very narrow diameter. When the valve closes, the disc descends deep into the seating area. A small movement of the valve stem causes a small, gradual change in the flow rate through the valve, which makes the valve capable of precision throttling. So needle valves are often used when precise regulation of flow is needed. Many globe valves, especially those used in steam systems, have a back seat that provides a seal between the stem and the bonnet of the valve. When the valve is fully open, the raised disc seats against the back seat. This prevents system pressure from building against the valve packing and keeps fluid from leaking into the upper part of the valve. In most globe valves, fluid normally flows up through the seating area and against the entire surface of the disc, making two nearly right-angled turns. Regardless of whether the valve is fully open or partially open, fluid flow contacts all the surfaces of the disc and seat, so wear on the valve parts is relatively even. As a result, even after it's been used for throttling for long periods of time, a globe valve can usually retain its ability to close completely. In this part, we'll look at plug valves, ball valves, and butterfly valves. A distinctive feature of these valves is that none of them has a disc that moves up and down from the valve seating area. Instead, each type has a disc that rotates. The rotating disc enables the valve to be opened and closed more quickly than many other types of valves. Also, the valve seat for a plug valve, a ball valve, or in this case, a butterfly valve, is usually made of a resilient material, such as plastic or rubber, that provides a firm fit and a tight seal when the disc closes on it. An operating lever or handle is used to position the rotating disc of a plug, a ball, or a butterfly valve. For instance, when the handle of this plug valve is turned, the disc rotates 90 degrees from the fully open position to the fully closed position, or vice versa. You can determine the position of the valve by looking at the position of the handle. When the handle is in line with the piping that the valve's attached to, the valve is open. When the handle is perpendicular to the piping, the valve is closed. Plug valves are generally used for on-off control in applications that require a tight shutoff, as in this gas line. When the handle is turned, the disc makes a 1/4 turn that quickly opens or closes the valve. When a plug valve is fully open, the ports in the disc, or plug, are lined up with the inlet and the outlet of the valve body so that fluid can flow through the valve. When the valve is fully closed, the plug is turned so that its ports are perpendicular to the valve body's inlet and outlet. For proper operation, the plug has to be able to turn in the seat, but the plug and the valve body must fit closely, so there's no leakage around the plug when the valve is closed. Because of the close fit between the plug and the body, the turning of the plug can gradually wear out the plug and the valve body. If either of these parts wears excessively, it may no longer be possible to completely shut off fluid flow when the valve is closed. Many plug valves, as well as other types of valves, use some means of lubrication to minimize friction between the valve's moving parts. However, some plug valves don't require lubrication. This plug valve, for example, has a plug that's enclosed in a sleeve that's made of a Teflon-like material, which is self-lubricating. Non-lubricated plug valves are especially useful for applications in which lubricant must be prevented from contaminating the fluid that moves through the valve. Like a plug valve, a ball valve has a disc with ports that are aligned with the inlet and outlet of the valve body to either allow or stop flow through the valve. As its name indicates, a ball valve's disc is called a ball because of its shape. The ball is highly polished, and its surface is smooth and uniform. A ball valve's disc fits snugly into a ring-shaped two-part seat. The two parts of the seat are called wipers. They're usually made of nylon or another elastic, self-sealing material that prevents leakage. One wiper fits on the inlet side of the body, and the other fits on the outlet side. During operation, there's little friction between the highly polished, smooth ball and the wipers. So ball valves generally don't require lubrication. Ball valves are commonly used for on-off applications. This is a butterfly valve. Butterfly valves may be used for various purposes, but they're normally restricted to low-pressure, low-temperature systems, such as a low-pressure gas line or a cooling water system. They're particularly useful on large volume systems where space is limited. Like plug valves and ball valves, a butterfly valve also uses a disc that rotates. However, the disc in a butterfly valve does not have ports. Instead, the valve has a thin, flat, circular metal disc that is rotated to open or close the valve. The round body of a butterfly valve is also relatively thin. So this valve takes up much less space in piping than many other types of valves. The rate of fluid flow through a butterfly valve is adjusted by using the handle to change the angle of the disc. The handle is a lever that may include a spring-loaded locking device. To change the position of the valve's disc, compress the lever and turn the disc to the desired position. A lever with a locking device is frequently used as the handle on a butterfly valve because flow through the valve can sometimes cause the disc to flutter or change positions. Locking the lever in place helps the disc resist the force of the fluid flow and stay in the proper position. A diaphragm valve has a bell-shaped bonnet and a body that looks like two pipes that curve into the bonnet. As its name suggests, a distinguishing feature of a diaphragm valve is a flexible diaphragm that's used instead of a disc to seal against the valve seating surface. A diaphragm valve also has no packing. Packing isn't necessary because the diaphragm forms a boundary that keeps fluid from leaking along the stem. A diaphragm valve has a part called a plunger that's connected to the valve stem. A diaphragm stud connects the diaphragm to the plunger. When the hand wheel of a diaphragm valve is turned in the closed direction, the stem and plunger are lowered. The plunger forces the flexible diaphragm down against the valve seating surface, which stops flow through the valve. When the hand wheel is turned in the open direction, the diaphragm moves upward, allowing fluid to flow through the valve. The diaphragm in a diaphragm valve isn't subject to uneven wear. So a diaphragm valve can be used both for throttling and for on-off service. The diaphragm also makes a tight seal that keeps fluid from contacting the operating parts of the valve. For that reason, diaphragm valves are commonly used in applications that involve corrosive materials and abrasive slurries. In addition, some diaphragm valves have protective liners made of plastic or a similar material. The liners protect the diaphragm and the valve body from damaging fluids. In short, diaphragm valves are widely used throughout industrial facilities for a variety of applications, but they're particularly useful in systems that carry chemicals or hazardous gases. A check valve is designed to allow flow in one direction only. It prevents backflow, which is the reversal of fluid flow in the piping to which the valve is connected. As long as it's in proper working order, a check valve operates automatically in response to system conditions. The valve remains open as long as fluid flows through it in the specified direction. But if fluid flow stops or reverses, the valve closes immediately. The body of a check valve is similar to the body of a globe valve, but most check valves don't have stems, handles, or hand wheels. Most check valves do have replaceable seats, discs, and caps. The cap is the top part of the valve body, which can be removed to provide access to the disc for maintenance. It's essentially the same as the bonnet on other types of valves. Several different types of check valves are available. We will look at three of the most common. The disc in a swing check valve is hinged at the top of the valve body by means of an arm and a pivot pin. When fluid enters, the disc pivots or swings away. This opens the valve and allows fluid to flow through. The flow through the valve is fairly straight, so there's minimal pressure drop across the valve. As long as flow is constant, the disc remains raised. If the flow stops, gravity and the change in fluid pressure pull the disc onto the seat, closing the valve. If flow reverses, the backflow pushes the disc against the seat to close the valve. If flow is intermittent, the resulting turbulence can cause the disc to alternately rise and fall or slam against the seat. The disc's repeated impact against the seat is called disc slam. Disc slam can damage the disc and the seat and result in leakage around the disc. For this reason, swing check valves are generally not used in applications where intermittent flow is common. A swing check valve, like other check valves, must be installed so that the direction of flow is under the disc. This disc position is necessary to allow fluid flow to raise the disc. It's also necessary because the disc depends, in part, on the force of gravity to pull it down onto the seat. The direction of flow for a check valve is often shown with an arrow cast into the outside of the valve body. As with any type of check valve, the disc in a horizontal lift check valve is positioned so that fluid will flow under the disc. When fluid enters the valve body and system pressure is greater than the weight of the disc is lifted off the seat. Fluid flows through the valve, then on through the outlet. When system pressure is reduced or flow is reversed, the disc moves down onto the seat. Another type of lift check valve is a vertical lift check valve. Fluid flows through this check valve vertically, but the disc is still positioned so that fluid flow is under the disc, just as it is in other types of check valves. A variation of the lift type check valve is a ball check valve. As its name indicates, a ball check valve has a ball-shaped disc. Ball check valves can be designed to operate in either the vertical or the horizontal position. In this example, the valve operates horizontally. When fluid flows through the valve, the ball is pushed out of the seat by the pressure of the flow. As the ball is lifted, it also rotates in the fluid flow. Solid materials in the fluid can't easily stick to the spinning ball. So this makes ball check valves excellent for handling liquids that contain scale and sediment. Because the ball rotates freely when the valve is open, the ball tends to wear evenly. When flow through the valve stops, the ball is pulled onto the seat. A different surface area of the ball falls onto the seat each time flow stops. This produces a self-cleaning effect that also helps to ensure that the valve continues to close properly. If flow reverses, the backflow holds the ball firmly on the seat, keeping the valve closed. Many valves can be opened or closed manually with a hand wheel. Ordinarily, the hand wheel is located so that the person operating the valve can apply the proper force to turn the wheel. In some situations, however, this isn't possible. Often, valves must be located in relatively inaccessible places. When this is the case, adapters may be attached to the hand wheels so workers can operate the valves. A common example of such an adapter is a chain that runs through a pulley. You must always use the correct size valve wrench for the job. Attach the wrench securely to the hand wheel so the wrench won't slip off while you're applying force. Never apply excessive force when you're opening or closing a valve with a wrench. Too much force could bend or break off the hand wheel or the stem. Excessive force can also damage the valve seat and the disc. Whenever you must operate a valve manually, follow the proper procedures to ensure that you don't damage the valve. If a valve is opened with a single operating lever, such as the handle on a plug valve, simply move the handle in the open or the closed position to operate the valve. If a valve has a hand wheel, use both hands, placing one on each side of the hand wheel, to open or close the valve. This enables you to apply force evenly to the valve. If force is applied unevenly, the valve stem can be twisted, bent, or broken. When a hand wheel is used to operate a diaphragm valve, excessive force could cause the diaphragm to jam into the seat and be cut, resulting in leakage. Finally, to check if a manually operated valve is closed, try turning the hand wheel or handle in the proper direction to close the valve. This prevents undesired flow through the valve if it's already tightly closed. Many valves can be operated manually with hand wheels or with operating handles. But valves often use mechanical operators or actuators to open and close. With these devices, valves can be turned on, off, or throttled more quickly and easily than with manually operated devices. Also, when mechanical operators are used, valves can be repositioned from a central, remote location, such as a control room. Common types of mechanical operators include pneumatic, hydraulic, and electric. Pneumatic operators, or actuators, use air pressure to produce motion that positions a valve. There are several different kinds of pneumatic operators. A diaphragm actuator is a pneumatic operator that uses air acting on a flexible diaphragm to position a valve. The diaphragm is raised or lowered by variations in applied air pressure. There are different designs of diaphragm operators, but they all allow flow to be automatically regulated as system conditions change. So these types of operators are often used for throttling valves. Typically, the diaphragm separates two chambers within the body of the mechanical operator. A spring holds the valve open or closed, depending on its design, when no air pressure is being exerted on the valve. Disc movement is adjusted by varying the air pressure that's applied to the diaphragm. As air pressure is changed, the valve is opened or closed. This piston actuator is a pneumatic operator that uses a piston inside an airtight cylinder to position a valve. It's generally more suitable than a diaphragm actuator for jobs that require relatively long stem travel or more force to position a valve. This vane actuator is a pneumatic operator that uses air pressure against a vane or paddle to position a valve. This type of pneumatic operator is used primarily with ball, plug, and butterfly valves. A hydraulic operator uses the pressure of a liquid against a piston to position a valve. A hydraulic operator generally develops more force than a similarly sized pneumatic operator. Some of the force exerted on a pneumatic operator is used up in compressing the air in the operator. But since, for the most part, liquids aren't compressible, more of the force exerted on a hydraulic operator goes directly towards positioning the valve. The power supplied by hydraulic operators makes them very suitable for the operation of large valves. This is a cutaway illustration of a single-acting spring-return hydraulic valve actuator. Fluid enters the cylinder of the actuator through a port and acts on only one side of a piston. The piston can be positioned anywhere in the cylinder by controlling the amount of fluid in the cylinder. If the hydraulic fluid pressure is lost, the spring causes the valve to fail closed. This is a double-acting hydraulic valve actuator. Fluid can enter the cylinder through either of two ports. The amount of fluid filling the cylinder and being bled from the cylinder is controlled to position the valve. If fluid enters through the top port, the piston is forced down to close the valve, and an equal volume of fluid is vented through the lower port. Increasing fluid pressure through the lower port moves the piston up, opening the valve. At the same time, an equal volume of fluid flows out of the upper port. When the flow of fluid through the lower port stops, the piston is essentially held in place by the fluid that is trapped on both sides of the piston. An electric operator uses electricity to position a valve. There are various designs for these types of operators. One type of electric operator is a solenoid actuator, or simply a solenoid. It's used for on-off control of a valve. Because solenoids can go from fully open to fully closed quickly, they're particularly useful for emergency shutoff valves. But because they have no intermediate or in-between position, they can't be used to throttle a valve. Valves that have to be throttled often use operators that are driven by electric motors. The electric motor drives a set of gears that controls the travel of the valve stem, which, in turn, positions the valve. When the motor is energized, the valve stem begins its rotation to raise or lower the disc. Enclosed in the body of many electric motor operators is a torque switch, a limit switch, or both, to ensure that the valve is positioned properly without being damaged. This is a torque switch. Basically, torque is a turning or twisting force. A torque switch cuts off electric current when the amount of turning force caused by the motor reaches a preset limit. This is a limit switch. It cuts off electric current to the motor when the valve reaches a preset position. A limit switch may be used to indicate the position of a valve and to ensure that power is stopped when the valve is in the fully open or the fully closed position. Some electric motor operators can be operated manually with a hand wheel if necessary. Typically, the motor operator has a lever that connects the hand wheel to the gears and at the same time disconnects the motor from the gears.